Let us begin. We will switch now. We will continue with probability theory, but we're done with the annoying calculations of looking at the sample space, counting the entries in the sample space, and figuring out what the words mean, and all of that trickery with probability questions. We're going to anchor ourselves a little bit more in probability. We will introduce what's called discrete probability distributions before we get to continuous probability distributions, which are truly the GOAT for statistical inference. But we'll start with discrete just for historical reasons, and also a lot of problems you can solve are actually discrete. There's really continuous is an approximation that makes the math a little nicer, but most things are actually discrete. So at the end, you'll be able to do the following: define discrete continuous random variables, define what a probability distribution is and what a cumulative distribution is, compute binomial, hypergeometric, and Poisson distributions and their associated probabilities. So we'll learn about 3 distributions. Compute the expected value, variance, and standard deviation of these distributions. Because once we switch to distributions, you start asking about statistics of the distribution itself rather than just a set of discrete data. Identify when to use which probability distribution, and define what's called a probability mass function. And a probability density function, we're not going to do this year. We will just mention it, but you'll define it in the next chapter. Okay. So what's a probability distribution? We know actually what it is. Remember those frequency tables we did in the past, early on with descriptive statistics? We had an interval, a range of salaries, for example, and a number, a count. And then I asked you to do a relative frequency count, where you took the count and divided by the total number. That gave us a percentage. And we said, oh, those with the salary between 50 and 60,000, there's 12%. Okay? Well, if you call that 12% a probability, and instead of having a range, you just have one number in that table, then that's nothing more than a probability distribution. Okay? So a discrete probability distribution is really nothing more than a relative frequency distribution designating the relative frequency, which we will call probability. Remember, in our definition of probability, we had the number of events over the total number in the sample space, right? So that's a relative frequency, right? So for example, we'll work this with an example and then build up. It's a very inductive process, and then build up all the definitions we need. So we will start by assuming that you're playing a coin toss challenge. You have 3 coins, and you're going to flip all 3 of them. Okay, so let's say you stack them on top of each other, or you somehow put them, laying next to each other on a little ruler, and you just kind of flip them. If all 3 coins land the same, either heads or tails, then you win $3.50. That's a lot of money in 1950s dollars. Okay, so that's a lot of money in let's say $35. Okay, otherwise you lose $1. Okay, so it's a gambling game. You go and flip the 3 coins. Okay, if you get all heads or all tails, you win $3.50. If you lose, you pay $1 just for participating in the game. Now, there's no cost to participate in this game, and the question is, what is the probability of getting 3 heads or 3 tails in a given toss? So we understand how to do this. We can write down our sample space. We could have all heads, or 2 heads and a tail, 2 heads and a tail, 2 heads and a tail. The order doesn't matter here because it's either 3 heads or 3 tails. And then 2 heads, 2 tails and a head, 2 tails and a head, 2 tails and a head, and then 3 tails, right? So in this case, order doesn't matter. So we can combine these these events together, HHT, HTH, etc., for all 3 coins. And then you can build a probability for all of these options. So the probability of getting 3 heads is 1/8, because you have 8 entries in your sample space. Only one of them is 3 heads, so 1/8. The probability of HHT or HTH or THH, because there's 3 of them, right, is 3/8. Same thing for 2 tails, getting 2 tails and 1 head. It's 3/8 because there's 3 of them. And then finally, the probability of getting 3 tails is 1/8. So we're not doing anything new over here. We know how to do this. I'm just kind of setting up the problem, right? Next, I want to take this one step further, and I want to plot this. I like to visualize things. I understand images easier than just numbers. Okay, and what would you do if you wanted to plot this? So first, what kind of graph would you do if I give you these values? Okay, what kind of graph would you choose?
A bar chart?
Bar chart, excellent. Okay, not a histogram because you already have the probabilities. If you wanted to do a histogram, you'd have to somehow put in HHH, HHT, etc., to convert those into a number and then just look at the frequency. The right way to do this here is with a bar graph, because you have the x-axis, you have 3h, and then 2h, and then 3t's, and then 2t's, and then you somehow put that on the x-axis and draw the probabilities as bars. Now the challenge is going to be on the x-axis. What do we put on the x-axis? HHT, THTH, and whatnot. Those are strings. They're letters. They're not going to be conducive for doing numerical mathematics. So we need to assign a number to those values. So because we're doing math, we can be very creative. We're going to declare, make a declaration that we will call a new variable, call it capital X, be a new variable, and let's say, on the x-axis, we can just put the number of heads in each of these options. Or you could choose the number of tails. Okay? So, for example, for TTT, X is equal to 0 because there's no heads. For 2 tails and a head, all of these, they correspond to X equal 1. Right? It's just simply a mapping. Okay? When X equal 1, you know that these are events where you only have 1 head. So it's 1 head and 2 tails. That's the only option here. When X equal 2, you have 2 heads, right? So it's all of these 3 options. And that makes sense because these 3 options are together, right? They're the same. So X is equal to 2 corresponds to all of them. And finally, for 3 heads, X is equal to 3. So all I did here, I went from letters to a number. Okay? That's called a mapping. You're mapping the letters to a unique number. Okay, good, very good. Sometimes you will learn that you can map numbers to other numbers. That's what we can do as well. Okay? Now, to recast those probabilities, I'm going to put here a lowercase x variable, and I'm going to say here the probability, P, that capital X is equal to small x. Why am I choosing this nomenclature? This is the standard nomenclature in probability distribution theory. This is saying that is always referred to as a capital X. It can take on any value, but I'm saying here when it takes on the value of this x, I could call this A if I want to, P of x equal A, but it's just common to say P capital X equal X because this is still a variable. This lowercase x is still a variable. But when I say P capital X equals lowercase x, I'm saying what's the probability when my variable takes on a specific value. Okay? So in this case, when x equals 0, my probability is 1/8. So that corresponds to this guy. Okay? 1/8. And then when x equal 1, my probability is 3/8. When x equal 2, probability is 3/8. And then finally, when x equals 3, my probability is 1/8. And then I can draw a bar graph. Okay, so see where we were, where we started with a bunch of letters. And now finally, I have a bar graph that describes the frequency of getting 3 heads or not. Now, formally, x is called a random variable. Okay, and P of x, now notice here, P of x, there's no equal sign here. This is the probability of the random variable x. This is called a probability distribution. So once you take this random event of the 3 coin tosses, assign a number to it, a value to it, you automatically have what's called a random variable. the associated probabilities, when you compute them, of those random variables. That's called a probability distribution of the random variable x. So we'll define this a little more formally. A random variable is any function, and by function here is, I mean, not like sine of x or something, is any mapping that assigns a numerical value to a possible outcome from a sample space. Okay, so the same way we did, we said, okay, I'm going to assign the number of heads to be my random variable. I'm going to count the number. You could have counted the number of tails. Okay, in some other cases, you're going to be counting the sum of something. Whatever you want, as long as it results in a numerical value, okay, if your sample space is not numerical in the first place, or it has weird numbers like pairs, but then you're going to combine those pairs like we did with rolling the 2 dice, right? So when you take those and do an operation in them and result with a single number from a random event, that's called a random variable. A random variable can be continuous or discrete. If discrete, we call it a discrete random variable. So discrete is going to take on very specific values, 1, 2, 3, 4, or it could be 1.1, 1.2, 1.3, 1.5. Those are the only possible values. It's a finite number of countable values. They're discrete. There's nothing in between them. There are no numbers in between them. However, a continuous random variable can take on any value on the real space, in the real axis. Okay? You cannot count a continuous random variable. You cannot count the entries in a continuous random variable. That has insane implications later, but makes the math all the more elegant. But we'll get to that later. From now on, we will use symbols like capital X, capital Y, capital Z to designate random variables, discrete or continuous. I could tell you, consider Y to be the voltage or the current in the wires, the random current in the wires, coming on to the MEB building. Okay? Call that a random variable, Y. Now, Y will take on specific values of lowercase y. So that's the nomenclature we will work with, right? And here we're just focused on discrete random variables. Next, a probability distribution is a formula or a table like we just had earlier. We had just a table of values that return or gives the probability of every possible value small x of the random variable capital X. We say that P of x equals small x is the probability of the event lowercase x. So be careful. Again, the capital X just designate the name of the random variable. The small x is the specific value that is taken on by that random variable. Okay? We will also use symbols like f of x, g of x, h of x, etc. to designate probability distributions. This also means that when I say f of x, at a specific value x, this means that this is the probability of x equal to the specific value of x. Okay? We're going to use those interchangeably. Because later on, the binomial distribution, we're going to call it binom, parentheses, a bunch of things. But that's equal to the probability of the random variable equal that specific value. Okay? Similarly, probability distributions can be discrete or continuous. What we saw just now is a discrete probability distribution. For each value, there's a value for the probability. If the random variable is continuous, then we will have a continuous probability distribution. We'll learn more about what we name them in a bit. Okay? So today and in this week, we will limit ourselves to discrete distributions only. Okay, good. Now, this is the note here when we say that P of x equal x. Those are not the same x values, although they have the same name. They sound the same, right? The lowercase x is a specific value that the random variable capital X takes on. So we need to be precise with the math. If we're not precise, unfortunately, you can get into slippery slopes and screw up any derivations that we're trying to make. Okay, more definitions. They sound like obvious, right? But it's important to have that formalism. Okay. Now, here's something maybe new that you've for the first time you hear of. A discrete probability distribution is very specifically called a probability mass function, PMF. And I will explain, you'll understand why we call it a mass function when we hit continuous distributions, okay? So you have to bear with me, but for now, accept that it's called a probability mass function, while a continuous distribution is called a probability density function. And we'll understand the difference once we hit the PDFs. So PMF for discrete, PDF for continuous. This week we're dealing with PMFs. Now, because probability distributions represent random events, right, and they're counting the frequencies, the relative frequencies of when these events happen, they must obey the rules of probability. Otherwise, don't call them probability distribution. Call them a function or a distribution, but don't call it a probability distribution. So when you see a curve, don't immediately rush to say that this is a probability curve. A probability curve has very specific conditions it needs to meet. Specifically, that any probability for any of its values is always between 0 and 1. So those bars can never go above 1. Any one of those bars can never go above 1. So you could come and plot me a graph and say, oh, this is the probability distribution of the height distribution in this class. And then it's discrete. And then I see a bar that's above more than 1. Tell you, no, that's not a probability distribution. That's something else. It's a curve. It's not a probability distribution. So be careful, don't call it a probability distribution if it doesn't satisfy this first condition. And the second condition, that remember in the sample space, the sum of all probabilities, or the probability of the entire sample space, is 1. So if we add up all of the heights of the bars in that distribution, they need to sum up to 1. Okay? There is an equivalent of these for continuous distributions, but it looks very different. Okay? So, okay, be rigorous, because this is a very easy way. This is a low bar to tell if your bar graph is actually a probability distribution or not. All right, so let's start taking this up a notch. I want to build a probability distribution for the sum of two rolled dice. And we had this table last time. For the outcomes, we had the two dice, let's say red and blue. And then on the first column, I'm listing the sum, and then the events is in the second columns. So they could never sum up to 1. The minimum sum is 2. That's when you have 1 and 1 on either die. And then 3, you have 2 events, and so on and so forth. And so we did this problem last week. So here, what would be my random variable? I'm already giving you a hint. I want to build a probability distribution for the sum of 2 rolled dice. So what would be my random variable? The sum, exactly. Okay, so we say, let x. Mathematicians have a lot of power. Let x be something, right? It's like, let there be light, right? It's just very out of this world, seriously. Physicists don't, well, they assume, spherical chickens and stuff like that. So let x be the random variable that designates the sum of 2 rolled dice. Okay? And then from the table above, we know that x, excuse me, can take on only these values, 2. They can sum up to a minimum of 2, 3, and all the way to 12. It is discrete. I can count this set. They're fixed values. There's no, the die can land like on the side and just have like a 3.5. There's none of that. It's either 2 or 3 or 4. So it's a discrete random variable. And if you count up the probabilities, we did that last time. So for the sum of 2, we had 1 over 36. For the sum of 3, 2 over 36. And you see it climbs up. And then the most we had sum of 7. there's a 6 over 36 chance of landing 7, and then they start shrinking down again all the way to 1 over 36. It's a very nice, symmetric, unimodal distribution. And on the x-axis here, I have my random variable, which is the sum. So you can read this very, very easily. For the sum of 2, I have about less than 0.03 chance in getting the sum of 2. And the chance increases as I get closer to 7. And then it shrinks again all the way down. It's very symmetric. The y-axis, it never crosses 1. So that's a good sign that this is indeed likely a probability distribution. The one that seals the fate, if I sum these up, 1 plus 2 plus 3 plus 4 plus 5 plus 6, etc., they do sum up to 36 over 36, and they sum up all to 1. Okay? So yes, it is indeed a probability distribution, and by construction. Now, if you had made a mistake, you'd be able to check that. But yes, this is a probability distribution. Okay, great, nice. Next, I want to open your mind about random variables, okay, and about that mapping that I mentioned. I don't know what happened. Mortimer. What? Huh? Okay. So you can be very creative in how you assign what your random variable, what you want your random variable to be, okay? And I'm going to go back to that example of the coin flipping and ask the question if it's worth playing that game or not. So we'll go back to that coin toss game, and the question is, if you play this game a number of times, are you going to come out winning or losing? So remember, you win $3.5 great dollars if you land 3 heads or 3 tails, and you lose $1 if you land any of the other ones. And remember, those were our probabilities. Our random variable here was the number of heads, okay, from going from 0 to 3, and the associated probabilities. In this case, you win 3.5. In this case, you lose 1. In this case, you lose 1. And in the final case, you win 3.5, okay? So for this problem, we need to estimate the average cost of playing this game. So how would you do this if you have this information? Go ahead.
You could multiply 1 divided by 8 by 3.5, subtract 3 divided by 8 times 1, subtract 3 divided by 8 times 1, and then
yes, 100%. Yep. It's essentially a weighted average, right? It's a weighted average. We've done that before. It's a weighted average. Your weights are these probabilities, okay? But the values are these guys. But wait a minute. We have an issue here because this is my random variable, not this one, okay? This is my random variable. So if I'm drawing a frequency table and I'm multiplying weight by I need to multiply the weight by the random variable, not some others. We have this additional value here, right? So we need to change this problem. You're correct. The answer is correct, but we can't do this every time. What would be better and more rigorous to use all the formulas we want to use later is to somehow have my random variable directly tied into the dollar amounts, right? And that's why I want to open your mind about random variables. You can create any mapping you like. So how about we do this? We create a new random variable, call it W, capital W, for winning, okay, or wins. Okay? And then for this W, I'm going to say, okay, there's 2 values only, either plus 3.5 or minus 1. What's the probability of winning 3.5? It's 1 over 8 plus 1 over 8. Right? Because there's 2 ways I can win 3.5. What's my other value of the random variable? W, minus 1. And for that, I can lose $1, 3 over 8 plus 3 over 8 times, or 3 over 4. And now I have a new probability distribution where the random variable is W, which is minus 1 and 3.5. It's a discrete random variable. It takes on only 2 values. Okay? And it has probabilities 1 over 4 and 3 over 4. And this is the probability distribution for this random variable. Is this legit? Absolutely, 100%. And it's actually more rigorous to do the math that your colleague just did on this problem. Because now I have the weights and the variable. So I can multiply whatever here. 3 over 4 times minus 1 plus 3.5 times 1 over 4. And that would give me that average, or the average cost of playing this game, without having to jump from 3 heads to 3.5, 1.8, plus, minus, etc. I just created a new random variable. This is a probability distribution. It never goes above 1. They sum up to 1. So it is indeed a probability distribution of the winnings or losings in a game. The point here is not to specifically, go after this problem. It's just to tell you that you can create whatever random variable you see fit, as long as it makes the math easier for you, as long as it allows you to get the answer cleaner. Okay? So now the problem, you can restate it this way. In this game, you have a 25% chance of winning $3.50 and a 75% chance of losing $1. Okay? Would you play this game? Well, we can do the calculation. If you do it, we have a 25% chance of winning 3.5 and 75% losing $1. And if you do this calculation, you actually come out ahead. There's you're winning $0.125 if you play this game. Now, we will later explain what this means actually on the next slide and later when we get to continuous. Now, on average, we would say you're winning 12.5 cents per game. So if you play this for a long time, you are going to come out ahead winning. Although your chance of winning $3.50 is only 25%, but the fact that it was $3.50, so it makes you a winner. Now, if you're a casino owner, right, and you want to design this game so your players lose, you would come to this formula and say, no, the house is losing all the time. So what would you do? You would change this guy, shrink it, or make this guy larger, just by a little bit. So you give the illusion that the players are winning some of the time, right? But overall, in the long term, they will be losing. Okay. Now, what we just did is nothing more than a weighted average, a weighted mean, which we know how to do, which we did that with the tables. We're just going to formalize it now, because now I have a random variable and a probability distribution, right? So we're going to start talking about probability distributions and what the weighted mean means for the probability distribution. In this case, this is called the expected value, specifically the expected value. We call it the mean value. But I think the word expected value has more meaning, because what are you expected, in this case, how much are you expected to win if you play this game for a long time? Okay? If you play this game for a long time, how much are you expected to win? So we define this as, so we've seen this formula before. Remember, we had summation of xi times f sub I. The frequency times the variable value, right? Or the center point of the range. This is the formal definition of all of this. This is called the expected value, or the mean for a probability mass function with a discrete random variable x. We call that mu, because this is a distribution. It means we know everything about the population. Okay, this is not a sample of data. This is the full distribution. We know everything, so we're going to call that mu. Now, it's not a sample, and it's written as capital E of x. So that's the expected value of x. And by definition, this is a definition, it's the weighted mean of all your random variable values multiplied by their associated probabilities. So these are the weights, and these are the values of your observed random variable. Okay? xi is the i's value of the random variable x. So how do you do this? You have all your values in the random variable. Discrete, it's a bunch. If it's a few values, you just sum them up, multiply by p, and you get an answer. Okay. So let's do an example. Jim is trying to decide between two different investment opportunities. There's two plans, A and B. The two plans are summarized in this following table. The first column shows the earnings and the likelihood. The second column shows the likelihood of getting those earnings. So, $1,200, there's a 10% chance. $950, there's a 20% chance. There's a 40% chance of making 130, 10% chance of losing 575, and so on. And there's another plan over here. Okay, this is already a well-defined problem. This is your random variable. It's the earnings, and the probability is your probability distribution. They sum up to 1, right? 0.4, 0.4, 0.80. They sum up to 1. So it is a probability distribution. And you can run the calculation. You can do, the weighted average formula, multiply this by this, and then add them up. In Python, you just multiply the two arrays and add them up. And then you do the calculation, and you get plan A, you get $24.5 for the expected value. And, oh, sorry, I didn't ask the question. So, he's asking, which plan should I choose? So think of this as a long-term trial. He's continually investing money in these plans, okay, for a long term. What is he expected to earn in the long term if these are the probabilities? Well, you run the numbers and you get 24.5 for plan A and 322 for plan B. So from that perspective alone, plan B appears to be a little bit better. It produces, it's going to give him a better return. Okay. We're going to keep taking it up a notch. Next, we're going to talk about variance and standard deviation. Now, excuse me. So far, we talked about the variance and standard deviation of discrete data points. I'm giving you temperature data from sensors or radon data, just numbers, okay? I'm not giving you a probability, no frequency distribution, nothing like that, just numbers. And we learned how to calculate the standard deviation and variance in those cases. But moving forward, we're not going to have that situation. We're actually going to be modeling probabilities of things happening. So we're going to be dealing with a probability distribution. So you'll have a random variable and an associated histogram or bar chart or probabilities with it. Okay, so not just samples from sample data. The question is, okay, can we calculate a standard deviation in that case? Yes, totally. And the way to do it is similar to how we did the variance previously. I'll show you on the next slide a little comparison. But essentially, the formula given a PMF, a discrete probability distribution, P of x, with a mean value mu, which we computed previously, the expected value, then the variance is given by this summation of xi minus mu squared. Remember when we derived the variance formula, we put the mean value as our gold standard in the center of the data. Well, not the center. We treated that as where the data wants to gravitate to, okay, the mean value. So we took the difference between each and every data point, okay, with the mean value. But here you still you're multiplying by a probability that a certain xi is going to occur. Previously, we only had xi values, 1,000 values. Okay, 5,000 values. You compute sum of xi minus mu squared, and we divide it by n, right? This is a different formula. When you have the PMF, this is the formula to use to compute the variance. The variance is a property of the population. So we use sigma. Once you have the distribution, it means you have the population. Okay, we're using sigma, not s squared. We're using sigma squared. The standard deviation is sigma square root of sigma squared, and you just take the square root of the previous thing. So I'll give this example again. Which of the same investment plan the guy was doing, and we decided to go with plan B because it earns a little bit more. But then now the question is, which plan carries more risk? Plan A or plan B? And I'm asking you, you can measure, a very rudimentary measure of risk is variance. Is like how much sway do we have in these data? Are we losing a lot of the time, winning a lot of the time? How are these data spread and distributed? So if you compute the variance and the standard deviation for plans A and B, what you get is that about $869 for plan A and $863 for plan B. So they are about the same in terms of variance. It's a large variance, but it's not outrageously high, so I would stick still with plan B. Anyway, this is easy, but for what's going to come next, which is much more interesting. Now, I do have a question for you to think about. You might not have the answer right now. I'm still thinking about this as a homework problem or an exam problem, or you might be able to just answer it right now. So remember how I mentioned the previous formula for variance, where we had just data, a lot of data, and we defined the variance, and assume you had a census. Okay, you collected all the data of the population. Okay, everything, all the data points. To compute the variance for that census, you take the sum of all the data points minus mu, which the mean of the population squared, over the total number of subjects in the population. But now I'm coming and saying, well, no, this variance looks like this, summation of xi minus mu squared times a probability. And how does that formula above compare to the one below? Because I can see similarity. I can see xi minus mu squared up there too, right? But
yeah, I recognize that 1 over n itself is a decimal, so it's a probability. So I don't know how to connect that to the probability distribution. I just know that's a decimal.
that's the first step in that direction, to recognize that, yeah, if p was 1 over n, that kind of would make it work, but that you need to build on that argument. Got a comment? Yeah.
Top has to sum to 1 for the whole sample space, basically.
What, the top has to sum to 1? Which has to sum to 1?
Px equals xi has to sum to 1.
Okay.
So it's kind of just a different way of saying that's the whole sample space. So it's like it would be for the.
So can you show? Okay, so let me rephrase the question. Are these formulas equal? And why? Again, you're right, but there's one more step that you need to do, Sam.
So I'm just going to put the probability of all of the x values as 1 over 36. And then if we...
But this is in general. So okay, if you want to take the die
I'm
example.
gonna
Let's
take
take the die example.
die
Okay,
example.
1 over 36.
Because we know multiplication and addition is commutative, we factor out the 1 over 36, dividing everything by n.
Okay, so let me ask you this question. That's a okay. Yeah.
It's like that, but we did.
Okay, so let me ask you then this. In this summation, let's take the example of the sum of the die, okay? And I don't have graphics here because on purpose, because I want you to follow with me, and if this is going to be an exam problem or a homework problem, I want you to think about it at home. If I were to sample, so this is a population variance, right? So it means I'm getting all the numbers from my sample space, right? All the numbers. So if we were thinking about the sum of the two die, right? So I would have the xi's here would include 2, and then 3, 3, and then 4, 4, 4, because there's 3 4s, and then 5, 5, 5, 5, because there are 4 5s, and then 6, 6, 6, 6, 6, there's 5 6s, and so on, right? And it would just do this calculation, divide by 36. What about that one above? What is xi in the one above? What does it go over? Goes over 2 once. It goes over 3 once. It goes over 4 once. It goes over 5 once. But what does it multiply each one with? The frequency, right? The key here is that the endpoints of these summations are different. Up there, you are only summing over the instances of xi. You're going 2. How many times does 2 occur? You're going 3. How many times does 3 occur? You multiply by p. And so you get a repeated terms that end up adding up exactly to this one. These formulas are identically equal. Except up there, I'm saying, I know the frequency of each term, how often it happens. So I'm not going to add it 3 times. I'm just going to put it once and multiply it by 3. But over here, you're adding it 3 times, or you're adding it 4 times. But they both add up to be exactly the same. Okay? But they are equal. So if you don't even want to think about what I said, you're like, why is this formula different than this formula? They're not. They're equal. They apply to 2 different things. Okay? Here you just have all the data in your population, even if it's repeated. Up there, you don't have any repeated data. You'd have each value of the random variable once, but multiplied by the correct frequency. So it's as if you repeated it 3 or 4 times, or however you need to. Okay. So why do we want to work with probability distributions in the first place? The question is like, why did I introduce this concept, probability distributions, and we did those kind of formulas, and then we're like, what, we didn't even use them yet. Well, just bear with me. It's all going to come together, okay? We're just kind of collecting low-hanging fruit. But the big question is, why do we want to work with probability distributions in the first place? It's because we hate to compute probabilities for each and every problem. It would be so much easier to say and identify that, okay, these types of problems that we often deal with, flipping a coin or rolling a die, etc., well, they all belong to the same category of probability calculation. Wouldn't it be cool to just have one formula and just apply it over and over again to all of these problems? And that's one of the main ideas of working with probability distributions. And it doesn't have to be exact. What you will notice is that most cases in reality, we're already making so many assumptions about independence and fair dies and fair this and fair that and no bias. We might as well model something as assuming it has a certain probability distribution. And when I say probability distribution, it means, these certain values, they have these certain probabilities pre-assigned to them. And when I say model, I mean we approximate. We assume that, okay, going and picking two random pieces of cereal from the shelf out of 12 pieces of cereal, and there's a gift or something, is a good example of a hypergeometric distribution. And just move on. Okay, that gives you the probabilities. You don't have to think about sample spaces, etc. All you focus on is the properties of your probabilities. Now, what's also advantageous is that the math and the results can be generalized. So for example, you can say, here's a specific example, that tossing a coin is a process that's governed by what's called a binomial distribution. We know the formula of the binomial distribution. We're going to develop it. And that binomial distribution always has a mean value of n times p. We'll learn what n and p are. And the variance is np times 1 minus p. Okay? Always, for any binomial process. So you don't have to repeat the calculations over and over again. So that being said, we'll start with the binomial distribution. So we will learn about 3 distributions, discrete distributions, that can be used to model a variety of things. We'll do examples on those. And they're more important, but they're mostly just as a segue to get us into continuous distributions. The binomial distribution models situations with a fixed number of independent trials or experiments. So for example, flipping a coin, rolling a die, or choosing something randomly from a bag. So that's a very common procedure. Okay? But the trial has only 2 possible outcomes. It's a binary thing, either success or failure. Okay, now how do you define that success? Doesn't matter as long as you call it success. Again, you have liberty in assigning what your random variable is. You could be checking whether batteries in your production process come out with volume greater than 11, with a voltage greater than 11.5 volts. Okay, and if it's less, then it's not 11.5. So you can say it's a success when it's greater than 11.5 and failure otherwise, or the other way around. Okay, so then you can use the binomial process to model that selection of the batteries, right? So you have that kind of freedom. In this case, the random variable tracks the number of successes. So by definition, the values that go into the binomial distribution, they correspond to what you call success. You could track failure as long as you just invert the meaning of those, and we'll see that once we define that binomial distribution. So here's an example. What is the probability of getting 16 heads when tossing a coin 58 times? Now, this is a binomial process. I can tell this because I've done this before, but it also obeys the rule of the binomial distribution. It's an independent trial. Tossing a coin is independent. Each time you toss the coin is independent from the previous one. There's only two outcomes, either heads or tail. I can call heads success and tail failure, or tail success, heads failure, doesn't matter. And now I have 58 trials. Okay, so I'm tossing the coin 58 times, and I'm asking what's the probability of getting 16 heads. Now imagine you wanted to do this with a standard probability calculation. You got to work out the math, and unless you're a probability guru, it's going to take you a minute to work this out. But with a binomial process, it's a simple one-line function call. You get the value, and you're done. Okay. Now, in this specific example, we are tracking the number of heads. So our random variable is the number of heads, and we declare that as the success. Okay, so let's get deep into the math. The formal definition is the binomial distribution is a discrete probability distribution. It's a probability mass function. It has a fixed number of independent trials. So you have to know beforehand how many times you're tossing the coin. How many experiments are you doing? And each trial has only two possible outcomes. And one of them is counted. You're tracking either heads or tails. And it's given by this formula, n choose x times p to the power x times 1 minus p to the power n minus x. Now, what do these numbers mean? We're going to explain them here. The experiment consists of a fixed number of identical trials. That's going to be n, that lowercase n. So in the previous example, I tossed the coin 58 times. N is going to be 58 in that case. Each trial is independent of the others. True. For each trial, there's only two possible outcomes. For counting purposes, one outcome is called success. The other is a failure. Okay. For every trial, the probability of getting a success is called P. And the probability of getting a failure is 1 minus P. So whatever you call success, assign it has a probability P. So in a fair coin, that P is 0.5. Okay? So heads or tail is not going to matter. But if you have a biased coin where the probability of success getting a head, let's say, is 60%, then you put 0.6 where P is. And then 1 minus P becomes 0.4, which is the probability of the failure getting the tail. The binomial random variable x counts the number of successes in n trials. So for example, if I'm asked, so I know n already, and I know what P is. X is how many successes will I get? What's the probability of x successes in n trials? So if x equals 5, what's the probability of 5 heads in 58 tosses of the coin? Okay? So n is given is how many times you're tossing the coin. P is the probability of your of success. Is it getting heads or getting tails? Whatever you define it, you just assign that the value of P. Okay? P always corresponds to the probability of what you call success. All right? And then X is your question. What is my probability of getting 5 successes in 58 trials? 10 heads in 60 coin flips. Okay? Once we do the math, once we do work out some examples, it becomes clear. All right. So X is the number of successes that you're tracking. N is the total number of trials. P is the probability of getting a success on any trial. Now, mathematically, we write this as B, X, semicolon, N, P. That's a standard nomenclature. I haven't seen any textbook that breaks this order, so this is true. X is the number of successes you're tracking. N is the total number of experiments you're doing. And P is the probability of each success. All right? We're going to do this in Python together. We're going to plot it. And in Python, if you want to Pythonify this, we're going to get into SciPy now. Okay? SciPy has a very good statistics library that is horribly documented. I don't know what these guys were thinking. It's the worst documentation ever. So you have to rely a little bit on what I show you in the class and possibly on Googling or using a ChatGPT, for example, to help you understand what some of the options are. I'll explain everything to you here in class, but if there's anything extra you want to do, you will find that the documentation is horrible. It's useless. But it's a very powerful library, very easy to use, very simple. It's similar to NumPy in how easy it is to use it. So you import what's called binom from scipy.stats. Okay, so you can just call this from scipy.stats, import binom, and you simply call binom.pmf. That gives you the probability mass function. Okay, for a given x, that's what you're looking for, number of successes, and number of trials, and p, the probability per success. That's it. That's all you need to do. And it's going to give you a value. What is that value? It's the probability of getting x in n trials. Okay, x successes in n trials. Now, this routine returns that probability of x successes in n trials, etc. Okay, so sometimes it can also be cumbersome to keep calling the full binomial each and every time. So let's say you already know you're doing 100 trials with a probability of success of 40%. Okay, but you're kind of trying to understand what happens, how was the probability of getting 5 successes, 7 successes, 10 successes, but n and p are always the same. It doesn't make sense to keep calling that function over and over and over and over again. It would be good and helpful if we were to just freeze n and p and only vary x, right? So you can do this by declaring binom np and putting that in its own handle, in its own variable, if you want. Call this my binomial. It's binom np. So you fixed n and p, and now my binomial is a binomial distribution with n trials and p probability for success. And next you call the PMF on my binomial, on your variable, and you say my binomial.pmf of x, and that gives you the probability. So then you declare this once. I know I'm doing the trial 100 times, 40% probability of success, but I'm going to try out what happens with 5 successes, 10 successes, 17 successes. You just keep calling this over and over again. It's easier and faster. Now, you can choose either. Yes?
Are you able to put an array in for x?
Yeah.
Okay, that's fine.
Yeah.
Do you have to like define n and p, or is it like in that order? You have to say like n equals.
Yes. Otherwise, yeah. It has. So those need to be values, right? So obviously in the code we're going to put in values here. Yeah.
But they're in that specific order.
In that order, exactly. Yep. Okay. So let's plot it together. Go grab a Jupyter notebook. So we'll do this and we'll be done with class today. Grab a Jupyter notebook. You should all have SciPy installed by default. Okay, so let me create a new Python notebook. Okay, let me turn. Sorry, I have to turn my back. Okay, and I'm going to, let's import NumPy as usual. Actually, let's just import the boilerplate. Let me go grab the boilerplate from somewhere here. We did. Pardon me?
The tried and true basic boilerplate.
Yes. I don't know if you have a better name for it. That would be cool. Boilerplate. I never, the what?
The ultimate answer to the star.
The ultimate 42. The 42. Okay. I had a hypothesis when we were looking to buy a house. Okay, sorry, you got me in. When we were looking to buy a house, I had this hypothesis. Every house has to have what I call the drawer of everything. It's like a junk drawer. It's got scissors, it's got scotch tape, it's got band-aids, it's got floss, whatever. And literally in every house I would go and look for the drawer of everything. And my realtor thought it was funny, you know. Anyway, you can laugh now. It's okay. Okay. So we import NumPy, etc., etc. All right. And does your house have a drawer of everything? Right? In fact, my wife was looking for the pulse oximeter to just kind of measure. We feel winded a little bit. She's feeling winded from the flu. And she's like, where the heck is it? I told her, let me check the drawer of everything. I think my younger son was using it as nunchucks. It has like this kind of lanyard to it, and he was like playing with it to try to like be Spider-Man or something as his brother. And I think he put it in the drawer of everything, and she found it there, actually. So, okay, so we're gonna import NumPy MP, and then from scipy.stats import binom. Okay. All right. So next we're gonna say, let's declare n to be 58 trials and probability b to be 0.5. Okay. And next I'm going to generate, I want to plot this. Okay. But before I plot it, let's just kind of see, let's just see how it works out. If I do binom.pmf and you put the function signature here, it's just useless. Look at that. K array like quantiles, what? And then star args, star k, double star k, it's useless. It's useless documentation, okay? Just use it the way I'm explaining in the notes, and that should be good. So let's say we want to look at the probability of getting 10 successes, let's say 10 heads, okay, in 58 trials, which is n, and then probability of success p. If you print this, it's just going to give you a value, okay? You know, the probability of 10 successes in 58 trials is 1.8 times 10 to the minus 7, okay? And let's see. The probability of 20 successes is going to be larger, 0.006, and so on. So it just gives you a number. That's how you evaluate this, all right? So the question I had was 58 successes, tossing a fair coin. What's the probability of getting 16 heads? It was going to be 0.0003, okay? Now, what I'm interested in, I want to visualize the binomial distribution. I don't care about the specific values, right? I want to see what it looks like, all right? Because that's where a little bit deeper thinking is going to occur. So to plot it, I need to generate a bunch of x values of successes, starting from 0 going to what's the maximum number of successes I can get? 58, right? Or n, right? So we can do this. Let's create x values, and those are going to be discrete. So it's going to be a NumPy discrete array. You can put them by hand, 0, 1, 2, 3, or you can use magic. There's a routine in NumPy called arange, for those who don't remember it. What does NumPy arange do? Look at how beautifully documented NumPy is. It returns evenly spaced values within a given interval. So I'm going to create an array of successes, possible successes, ranging from 0 to 58. Okay, and I want them to be discrete. NumPy arange does that for me. Start to stop, and stop is an open interval. So I need to go to n plus 1. And if you're in doubt, print it out. So let's try this one out. I'm going to go from 0 to n plus 1. And let's print them. Print x values. Look at that. 0, 1, 2, 3, 4, blah, 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 all the way to 58. What I'm going to do next is compute the binomial PMF for each one of those values and plot them. Okay? Someone asked, can we pass on an array? Absolutely. Binom.pmf x values, okay, and then np. Now, what is that going to give? It's going to give an array of probabilities. This is the value corresponding to 0 successes. This is the value corresponding to 1 success, to 1 success, 2 successes, 3 successes, and so on. Okay? So all we need to do next is plot this. We're going to make a beautiful, cute, what was it? Cute little plot. Thank you. Cute little plot. Okay, now we're going to do a bar plot. Okay, so plt.bar, I'm going to do a, not a perfect bar plot, but, we'll put the x values. And here, let's call this my probabilities. That sounds, the probabilities. Okay, the probabilities. Okay. And let's just see what it looks. Look at that. Very pretty. It's cute and little. Looks like one of those Art Deco buildings, right? Like the high-rise Gotham City structure. Very nice. Okay? Okay. Are we in sync? Okay, let me ask this before you go. What do you think is going to happen? So let's understand this. On the x-axis, I'm plotting the number of successes per 58 trials. To make this a little cleaner, let me just let's just do 10 trials. Okay? 10 trials so we can see these things better. Okay? What this plot is telling me, the probability of getting 0 heads is almost 0. 1 head, this is the probability. 2 heads is coming up to 0.05. 3 heads, it's higher. 4 heads, 5 heads is the highest. And then 6 heads is starting to go down. This is with a probability 50-50 chance. Okay? What happens, again, we're counting heads as successes. Okay? What happens if my probability goes higher? Let's say 90% or 10%. Is it going to shift to the left or is it going to shift to the right? Let's start with 10%. Let's say now I'm changing. Don't change it and look. I want you to think about the answer. If the probability of success is 10%, are we going to have a lot of successes? No. So what's going to happen to the curve? We're going to have a lot of little successes, okay, and not many high successes. Good. And the opposite is true. Let's try it. Let's try it, and you can be gone. 0.1? Yes. Correct. Not a lot of successes. Remember, the x-axis is counting how many successes we have. There's only a 10% chance of getting a success. So the number of successes is going to be low, not that many. Okay? 90% chance of success, we're going to have a lot of successes. Look at that. Okay? Thank you. I'll see you on Thursday. Godspeed.